let's recoup. So properties of power series. We're going to go and talk about the interval of convergence and radius of convergence. And the first thing is that we have to understand that the definition of the power series has that x in there, and the value of that x can greatly impact the convergence or divergence, whatever you pick for those. And we'll take a look at the examples. So to study interval of convergence, we are going to take a look at 3 examples that are very good. They will all be solved through ratio test. Ratio test is the boss in this case, so we always use ratio test, regardless of how problems look like. We'll see why. So the first example, number 1, is going to be to look at the series of x to the k over k factorial from 0 to infinity. So what I'm going to do is I'm going to do the ratio test, and then I want to see whatever I get from the ratio test, because I want to force convergence. I will force it to be less than 1 and see if x is always the number or in range. So we'll see how that works out. So let's go with the ak is x to the k over k factorial, and then ak plus 1 is x to the k plus 1 over k plus 1 factorial. To do the ratio test, we have that limit k goes to infinity of peel off 1, so x to the k divided by, don't forget the absolute values. Now this is, if you forget absolute values in this ratio test, you're dead, and you'll see why. You have to have it. K plus 1 times k factorial times, flip the other one immediately, close the absolute values. We're going to cancel k factorial, x to the k, x to the k. And we have the limit k goes to infinity, absolute value of x over k plus 1. All right, now, if you recall your calculus 1 limits, the variable for the limit is k, so x is just a constant, a parameter, so you can kick that in front of the limit. So you can kick absolute value x in front, and you should just have limit k goes to infinity of 1 over k plus 1. Now what is the limit for that? Limit for that is 0, right? So we have x times 0, which is 0, which is always less than 1. So what does that mean? It always converges, right? So regardless of what x you pick, this particular power series will always converge. Yes, ma'am? Oh, yes. So k plus 1 factorial is equal to 1 times 2 times 3 times 4 times dot 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 times k minus 1 times k plus 1 is the last term. Fair? Yeah. So would you agree that if I peel this last term, everything before that is k factorial? And then times k plus 1. Fair? Yeah. All right. Kill this. So I will write here that this power series converges for all x values. It doesn't matter what you pick for x. Once it's multiplied by 0, it will always be 0, it will always be less than 1, it will always converge by the ratio test. Does this make sense? So I can claim, since the series, what was the series? X to the k over k factorial? X to the k always converges. Radius of convergence sorry, interval. Let's first do the interval. Interval of convergence is infinite, meaning from negative infinity to positive infinity, which implies the radius of convergence is r equals infinity, also infinite. If you want me to put that on the number line, even though it doesn't make sense, this is where the 0 is. It converges from negative infinity to positive infinity, where the radius of convergence is equal to infinity. Now this will be much clearer in the next example. Next example is series negative 1 to the k, x minus 2 to the k, divided by 4 to the k from 0 to infinity. So, when you are dealing with a ratio test, you will always have absolute values. Whether you have positive 1 or negative 1, absolute value will always make it into a positive 1, so we don't have to worry about the alternating term for ratio test. It's cool.
So wait, can you restate what you just said?
Because we are using ratio test, and ratio test always has the absolute values, whether we put the alternating term in or not, it doesn't matter, because absolute value will kill it every time.
So for power series, you always use ratio test no matter what they're given?
Yes. So AK is going to be x minus 2 to the k over 4 to the k, and AK plus 1 is going to be x minus 2 to the k plus 1 over 4 to the k plus 1. We are going to write the limit. K goes to infinity, and we have the same rules. So absolute value, don't forget absolute values. They're not there for decoration, guys. You really have to have them. You'll see in this example. Peel off one of the x minus 2's, so you just get to the k. Divided, peel off one of the 4's, times, flip the other one. Right, we're saving a step by writing the division as the flip multiplication. And then cancel. So we have the parentheses cancel and the 4 to the k cancels. And look what you have. You have limit, absolute value, x minus 2 divided by 4 as k goes to infinity.
What did you do with the negative 1? Just don't need it.
So now, do you have anything to calculate the limit on for k? There are no k's, right? All of the k's canceled. So all we have now is just this expression x minus 2 over 4, and we set that less than 1, because we know that convergence for the ratio test happens for less than 1, limit less than 1. So now you have this algebra equation, well, inequality, which you need to solve. What does it say? It says x minus 2 over 4, absolute value, less than 1. That means that negative 1 is less than x minus 2 over 4 is less than 1. For those of you who forgot the algebra. That's the same statement. And then you multiply it through by 4. And then add 2. This thing over here is your interval of convergence. Interval of convergence. What does that mean? That means that if you pick any x between these two numbers, the power series will converge. Now, give me one of the values from there. 1. Thank you. Let x equals 1, just to prove my point. Our power series was summation 0 to infinity, -1 to something, to k, x minus 2 to k, divided by 4 to the k. I hope you guys see that once you plug in x equals to 1, this power series becomes just your regular chapter 8 series. You see that? Immediately becomes that. So let's show. So if x is equal to 1, the power series is going to be 0 to infinity. You have -1 to the k times -1 to the k divided by 4 to the k, which is series of 1 to the k over 4 to the k, which is the series of 1/4 to the k. What kind of series is this? Yeah, it's geometric series less than 1. It converges. It better converge because we picked x, so it does converge. Now, if you give me anything out of the bounds, -2, +10, +100, it must diverge. It must diverge. So converges by stuff.
How did you know to multiply by 4 and add 2?
Multiply by 4 and add 2. I'm sorry?
So that you will-
You mean this?
Yeah.
I'm just solving equation for x.
Moving over the 4.
Yep, I'm getting x alone, right? I'm getting x alone. That's all I'm doing. So let x equals to 10. What do we get? We get series of -1 to the k, and then 8 to the k divided by 4 to the k. I said 4 to the k. Do you guys see that that 8 over 4 is 2? That's bigger than, right? Bigger than 1? It has to diverge. It has to diverge. So if I pick a value for x, so the goal of this x over here, the goal of interval of convergence is to show what are the values of x that you are allowed to pick, and no matter which one you pick from those values, you will always have the power series convert into regular series, and then that series would converge. If you pick anything else, then in that case, the power series will diverge immediately. Does this make sense as a concept? Now, what is the radius of convergence? Well, 2 and 6 are 8 units apart, so 8 units divided by 2 is 4 units. So radius of convergence is 4. Let me just write that down. Yes?
I just have a question on like chapter 8 for that.
Mm-hmm.
So the -1 to the k still has no effect, even though they're the same.
No.
It's
When
still the absolute value?
Yeah.
Okay. Oh, because
If you are to put all of this stuff together, you would remember for let's just solve this. So if I use just algebra says that I can have all of these mushed together to the single k power because all the powers are k's, right?
Yeah.
So I have -8 divided by 4. I have -2 to the k. And if you recall from the theorem, it says that if the r is bigger than 1 or less than -1, it diverges. And if it's between -1 and 1, it converges, right?
Yeah.
So this is on that other end that we usually didn't use.
Yeah.
So it's there, right? So it's divergence by geometric. Both of these, converge or diverge by geometric. So since interval of convergence, the IC, is -2 less than x less than 6, radius of convergence is r equals to 4. R equals to 4. Interval of convergence. And again, I can graph this. So here is -2. Here is 6. And that's 8 units apart. This is where the 0 is. So if you go 4 units this way, go 4 units that way. So this is the radius of convergence, and this is the interval of convergence. So radius gets to be centered in the middle of the interval. Radius gets to be centered in the middle of the interval, and then it goes both sides, left and right. Sounds good? All right, so how are these two problems different? Well, the first example I did, we had that the interval of convergence is infinite and the radius of convergence is infinite. That means that any x I pick under the sun will make this into a convergent series. Where the second problem clearly gives us the range and says if you pick from these numbers, you have convergence. Anything outside of that range is going to be divergent. We have one more case to worry about. Now, if you use common sense on this one, you might get it wrong. The common sense should say what? Right, we had converges everywhere. We had converges somewhere, and this one could say converges nowhere, right? But unfortunately, it's a wrong answer. So let's discover that. We are going to use ratio test again. AK is k factorial x to the k, and AK plus 1 is k plus 1 factorial x to the k plus 1. So limit k goes to infinity. Now I'm going to write them actually. So k plus 1, peel off 1, and then we just have k factorial times x to the k, divided by the good old k factorial x to the k, which is the original. You cancel k factorials and x to the k's, and look what you get. Don't forget your absolute values, otherwise you're dead. I told you that. You get limit k goes to infinity of k plus 1 times x, but before I multiply this, I kick x outside because it's not relevant to the limit. And I have k plus 1. Now what would that give me? Infinity. Right? But then, what if x equals 0? Then it goes down to 0, and it converges at that point. So, converges at the single point x equals 0, diverges everywhere else with radius of convergence r equal to 0 because one point has no length to it. So wow, cool, right? Have to be careful about that too. So we have converges everywhere, regardless of what x is. It has converges in a range, whatever range you calculate, and then converges at a single point and diverges everywhere else. Yes? Perfect. Yes, ma'am.
Do you have to write
that it diverges everywhere else, or you just assumed by that?
Mathematics showed it. What do you mean? Can you please repeat the question or restate the question?
Like, where do you have, like, written there that it diverges?
I didn't write anywhere that it diverges. What I did is I analyzed. I didn't assume anything. I analyzed this statement.
Oh, okay.
If x, I can pick anything for x.
Yeah.
I can pick pi. I can pick e to the pi. I can pick e to the pi squared. Doesn't matter, right? I can also pick 0. 0 kills the term. And 0 is less than 1, right?
Yeah.
Because if the x is 0, it kills the term, makes everything equal to 0. And in that case, 0 is always less than 1. So if I pick x equal to 0, it's going to converge because less than 1 ratio test. If I pick anything other than 0 for x, it's going to multiply into that infinity. It's going to blow up. It's going to be divergent. So it converges only at a single point. If for x equals 0, it converges. For x equals anything else, it diverges. So we say converges at a point, x equals 0. Cool?
Yeah.
So we have to worry about 3 things. One is it converges everywhere, it converges on the interval, and the third one converges at a single point. I mean, obviously diverges everywhere, those are easy. Yes?
How do you deal with recognize which cases?
Well, when you do the problem, it presents itself. There is no, recognizing it before or anything. You just do the problem, you do the ratio test, you know how to do that one, and whatever you get at the end is what you got at the end. It is either going to be convergent everywhere, which means you came up with a solution that is not dependent on x in any way. So no matter what you pick for x, it converged. And there could be where x weighs in to give you an interval, or it could be where you multiply, 0, and you get the convergence at a single point. So let's do more examples of this.
So you know it's the interval if there's no k in the limit once you do it.
Because you can't apply the limit in that case, because there's no k. K limit is only applied to the terms with k's.
Yeah. Yeah.
All right, so you guys want to try one of these? Let's go. All right, so let's try this one. Problem 16. 2 to the k, x minus 3 to the k, over k, from 0 to infinity.
The boundaries really have no meaning.
All right, try this problem. See how it works. So we first create AK. We create AK, we create AK plus 1. We do the ratio test right off the bat. Don't forget the absolute values. Follow the algebra. Step by step. So only if you have that minus 1 alternating term, you can skip out on it. The rest, yeah.
Put it that way. Just keep it. But there's no project. There's no project.
Yeah, no, I was just wondering. No, I was just making sure. But I'm not good at that. You have to use the yeah, that was
Okay, troops, let's take a look at this problem together. So we start with AK, which is as is, and then AK plus 1 is going to be 2 to the k plus 1 times x minus 3 to the k plus 1 over k plus 1. So we do the ratio test right away. We have the limit. K goes to infinity. Absolute value must be there. Don't forget that. Peel off 2 and then 2 to the k, and then you have x minus 3 and then x minus 3 again to the k. So I peel 1 off, right? And then divided by k plus 1. There's nothing you can do there. Times flip of this one. So there you go, to the k, and then x minus 3 to the k. Close absolute value. Thank you. So now we cancel these guys, we cancel these guys, and we have the limit. K goes to infinity. I have 2 times k times x minus 3 divided by k plus 1 in absolute values. Now, guys, remember, the limit applies only to k's, which means that everything else, if it's multiplied into those k's, can be kicked in front of the limit as the constant. So absolute value of 2x minus 3 gets kicked outside, and the limit of k over k plus 1 stays, but that's equal to 1. So what I get is the absolute value of 2x minus 3, and I set that less than 1 because I can, right? So now what do? I solve this. This is negative 1 less than 2x minus 3 minus 1. Now if you distributed these two, I don't care, whatever. You can divide by 2 everywhere, or you can distribute and then add and subtract, whatever you did. Negative 1/2 less than x minus 3 less than 1/2. And then when you add 3, right, you don't have negative anymore on the first term. So it's going to be 5/2 less than x less than 7/2, or those of you who use the mixed numbers, 2 and 1/2 less than x less than 3 and 1/2. So whichever way you did this. This would be the answer. This is our interval of convergence, IC. And if you look at this, the radius of convergence has to be 1/2 because these are 1 unit apart, right? 7/2 minus 5/2 is 2/2, which is 1. And then half of that is 1. So, and I can also do that graphically. I'll be right with you. So that's 5/2, and that's, let's say, 7/2. So right in the middle is 6/2, which is 3. So that's the radius of convergence. Now, I want to point now, because we have 2 examples, I want to point out something, but let me just get the question.
Can you scroll up a little bit to the one? How did you get so one is greater than the actual value function?
You mean this one?
Yeah, how did you get there?
That one I put myself because I'm looking for interval of convergence, and the ratio test converges when this absolute value is less than 1. So I am forcing it. I am placing it myself there, that less than 1, because that is the condition for convergence. Because I want to find the interval of convergence, I am forcing convergence by writing less than 1 there.
You get the limit of k over k plus 1. That doesn't work here at all.
It's 1, so I don't have to do anything with it, because the coefficients of 1 and 1, k and k is 1 over 1, which is 1, right? So there's nothing there.
So is like the end goal of it to get your R value after you have your range?
Once you have your range, yes, you figure out your R value. It's always the half of the interval, so you can always figure out how long the interval is, and then half of that. Now, guys, one very important thing that might slip before, when I was talking about, oh, we actually have, no, we have 2 examples. So please look at this. What does it mean, this minus 2? What does that do? Does anyone remember from the theorem from last time? What does it do? Yeah, it is a shift to the left, but to the right. But what does it mean? What is? I use the specific words. What is it? It is. What purpose does it have in our power series? That x minus a. So what's the purpose of that a? Well, they do meet there, but there is a specific word that you can say. Specific word you can say. The what? No. Nope. What is the purpose of this? Why do we even consider having that there? The question is, what is this 2 doing here? What is the purpose of the 2? Yes. It does shift it, but what does that mean? Why would we want to shift anything? Left or right? That's it. It's the center, right? Remember how when you are approximating sine with x, it was centered at 0. And all of the approximations, no matter how many terms we did, they went right through 0, and all of the approximations were very good in the neighborhood of 0, but they were very bad around 3. They were very bad around 10. So this means that because it's centered at 2, all of the approximations are going to be perfect at 2. Now, can you look at the middle of this interval? What's in the middle of this interval? 2, right? 4 from the left, 4 from the right. Whatever way you look at it, it's going to be 2. Last example, the one we just did. Centered at 3. What's in the middle of my interval? 3. You see the graph? Yep, that's one of the checks. It has to be your center of the power series has to be exactly in the middle of your interval of convergence, because your power series is centered at that value, and then you add and subtract the radius to get the interval of convergence. The very first example we did with infinity, it was centered at 0. And you have infinity to the left, infinity to the right. So that's one of the checkpoints that you guys can use to see if you did the problem correctly, at least to some extent. That's that. So I hope you understand the interval of convergence and the radius of convergence and what are they used for and what they're all about. Now we're going to jump into further properties of power series. We have to talk about combining power series. Yes?
Okay, do you want us to look and test the remainder stuff, alternating series, the remainder, and it's remainder terms, and we'll test the alternating series test?
I will talk about that when it gets done. We're getting there. So further properties, and that would be the combining PS power series. So if you guys understand what the power series are, power series, those that converge, if we know how to find the sum, they end up being a number, right? And what can you do with two numbers if the power series are convergent? You can add them, you can subtract them, you can multiply them, you can do the composition and all of that good stuff. So property says that supposed to, well, actually first let's put the, suppose the power series ck x to the k and dk x to the k, they're both centered at 0, but you can toss in minus a on each one, doesn't matter, converge to f of x and g of x. What does that mean? That means that they're, equivalents of, you have a power series that gives you sine, you have a power series that gives you cosine, power series that gives you ln, power series that gives you g to the x, and so on. So there is a correspondence between the power series and the function. So the sum and difference would work. So if you have the summation of ck x to the k plus or minus sum of the dk x to the k, you will get f of x plus g of x plus minus g of x. So they add. Number 2, the multiplication by a power. So x to the m power series ck x to the k is equal to summation c to the k x to the k plus m. That's, you can import this one because it's a summation, so it multiplies, distributes on each term. So that's something that you can do, which in fact is going to be the x to the m times f of x. And number 3 is the composition function composition. So if age of x is equal, and this we're going to use some of this stuff now. F of x is x to the b times x to the m, and m is a positive integer, so m bigger than 0, and b is a non-zero real number. B is different than 0. Then you have the power series ck, and now we do the function composition, which is age of x to the k. This used to be x, now it's age of x to the k converges to composite function f of age of x. Are you ever going to use this? Are you ever going to use this? And click. And there we go. Series solution to near ordinary solutions to ordinary differential equations near ordinary points. You have a second order linear differential equation, and then you assume that would be differential equations. No, you just get smack in the face right with it. Yeah. So I'm just telling you, look this stuff up before you take that course, and take the course here while it's still fresh. All right. So this is me teaching it, and as you can see, guys, in addition to you using the rules that I just wrote, there are some derivatives over here being taken, and you plug everything in, and then I make a mistake, and then I cross that line, and then we get into actually solving the problem. So guys, these rules that I just listed are here. You don't see them because this is way too busy, but these 3 rules that I listed, 2 out of 3 rules are in here. 2 out of 3. Number 1 and number 2 are in here. Being able to collect this term to get to the recursion equation. So all of this is one example. All of this is one example, and the final example is done. There it is. So what you guys need to do is to learn this stuff, so you don't get smacked in the head too hard with these things. Yeah. Now the problem is that I don't have all my differential equations lecture on this tablet, because this is the time when I got this tablet, so I was switching back and forth between 2 tablets, and I don't have the rest of the chapter 3. You can see that it's only have 3.2. There is 3.1, 3.3 missing. So there, chapter 3 is solving differential equations by using power series. You assume the solution. You assume the solution of this sort, which is the power series, as you can see. And then you take their derivatives, and then you plug them for all of these guys, and then you work out the magic from there. So there is a lot of this stuff used later on, and depending on how many and which math courses you take down the line, there will be more use of this. So, yeah.
So what are we trying to get at?
Solves differential equations.
Is it just no? I mean, what is different from what we did, those 3 things, and just power series? Is it just adding?
Those are the properties, right? You can add them, you can subtract them, you can multiply them, and you can do the function composition, because they are depicting functions.
It's pretty much multiplying, adding, integrals too.
Yeah.
You look at it like that.
So they're just like a little.
Yep. Well, once you read the stuff, try to understand those things, those problems. Obviously, it should work out. Theorem 9.5, it says differentiating and integrating power series. I'm going to give you a very short theorem there. So it's going to be, so theorem 9.5, it says differentiating and integrating power series. And here is my theorem there. Do it term-wise. And we're done. That's the theorem. So, I mean, they have a half a page there in a box, but just understand what you're doing, right? You take a power series, and we're going to have examples of this, obviously, coming up in last section. So you guys have you have a function, and you create power series of it, where you got the polynomial, and then you differentiate each term in that polynomial, or integrate each term in that polynomial. So there's nothing, you know. It looks impressive when you see the theorem that takes half a page with the box, but here, I'll show it to you. It's just, you know, this is what it is. That's how it looks like. But all of this says just do it term-wise. All right? Coming up in 9.4. These are just properties that are piling everything up, and then you can use it later. Actually, they do give you an example here, but we're going to do much more of this. So I'm just going to copy this example real quick. I don't know why, but So f of x is given as 1 divided by 1 minus x. And I'll just put insert work here. Because you need to do all of those derivatives and things to come up with the polynomial on the other end, which is x to the k, which is 1 plus x squared plus x cubed plus x to the 4th plus ... going forever. So looking at that, what is the derivative? You just differentiate each term in the polynomial. So instead of differentiating this using the chain rule, quotient rule, or whatever other witchcraft you might think of, you can differentiate these guys term by term.
How many times do you have to go?
Usually 3 or 4 for good precision. 3 or 4. This is Taylor series. Yep. This is Taylor series. There's nothing else out there. I mean, there are Fourier series and other series, but for us, the polynomial series, Taylor series. So. Oh, this is far cooler. Plus gives you something to explain to people during the Thanksgiving dinner, you know. Guys, I don't know why you don't use that, but as soon as someone tells you, hey, how are you doing, or what's new? If anyone ever asks you what's new, wasn't this new for you? It's new. Take the paper, take the pencil, sit them down, and show them what's new. Guarantee we will never bother you again. Exactly. Right? I know. So let's see, is this done? Yep, that's done. All right. So we're going to take a break now, and then when we come back, more of this stuff. We got to finish, do some examples and so on.